Yeah, thank you very much, Paco, and I also like to welcome everybody to this third and last section of this workshop. Indeed, I will talk about lossless LC filters and some properties who I discovered are often overlooked. And I also promised to talk about some miscellaneous problems, and I've been choosing to briefly spend some time on the notion of Kirchhoff operators and also gyrators and their relationship to reactive power. But let's start with lossless filters first. And this research came actually from also from my participation in the IEEE working group of the revision of the standard 1459. And one of the first sentences in this in this standard is what I put over here. And I changed it a little bit into my own notation and words, but it's more or less the content and the meaning is the same. And this you also see a lot in just standard textbooks, and also a lot of papers. And that is that under the assumption that a load or just an electrical circuit in general is linear. And then when you excite this with a purely sinusoidal voltage, then because of linearity, it is assumed that the current then also will be a pure sinusoid, of course, with a different amplitude than the voltage in general, and perhaps a phase shift. However, to ensure this fact, I mean, we actually need a couple of other assumptions which are in general not mentioned. And I will illustrate this with two examples, and I will start with just an example about a system which is often called nonlinear in the literature. And that is, for example, this very simple triac circuit. And so you have just a sinusoidal voltage source and then a resistor which is controlled by a bidirectional switch. That's the triac circuit. The principle of this kind of circuit you can find in the dimmers you have at your home most probably. Well, what you see here is that with the switch you can just cut off the current here at a certain at a certain moment in time, or at a certain firing angle. It's called. It's denoted by the little delta here. And what you actually see is that you have a sinusoidal voltage and you have a non-sinusoidal current here. And of course, because by cutting off this current, what you get is you generate odd harmonics in the current. And it's in principle an infinite amount of harmonic current components. And on the other hand, I mean, if you consider the relationship between the voltage and current, you can model this all the stuff here in the yellow box. You can also model this as a time varying conductance. And this conductance you can define like this then. They're just repeating blocks, depending on the fire angle. And well, it's zero when the switch is closed, and it will be 1 over R, the reciprocal of the resistance. When the switch is open, I mean here, of course, and when the switch is closed, then you have the reciprocal of the resistance. So that means that if you just write Ohm's law, essentially, you have this relationship. And now it's very easy to prove that this relationship is just linear. It's linear with respect to the current and the voltage. The only thing what is different from the normal linear and time invariant property is that we now have a conductance which depends on time. But nevertheless, I mean, relationship. So this circuit, although often regarded as being nonlinear, is a linear and time varying circuit, or an LTV circuit. Well, the proof of this, if you're interested, you can find in in a very recent paper by myself and my co-author Pablo Borja from the University of Groningen. We presented this at the EPQU conference in Poland. Well, there was also that I could not visit Poland; it was all online. But you can find this on IEEE Explore. Now, so this is one thing that you should be careful that even though a circuit might have like switches or what are often considered as non-linear elements. I mean, it doesn't necessarily have to be non-linear. I mean, you have to investigate it. So that's one thing, and this is of course, I mean, in contrast to what is stated in the IEEE standard. I mean, the circuit is linear. It doesn't talk about time invariance, for example. Linear. And then supplied by a sinusoidal voltage will always result in a sinusoidal current according to the standard. But this example shows, of course, that even that this circuit is linear, even though it's time varying. I mean, the current is non-sinusoidal. So that's example number one. Well, example number two, that's concerned with this lossless LC filters, and you see them appearing a lot in papers about power factor improvement under non-sinusoidal conditions. And here I just picked a few of these pictures just from papers, and perhaps you recognize that this is from Czarnecki's work, this as well, and this one. And these are from other papers. I just collected these figures, and you see everywhere that it's a pure LC filter that people are dealing with, and they approach the design of this filter. They approach it using phasor algebra. Well, in principle that's okay, but you have to impose a few assumptions here, which are actually very difficult to accomplish in practice, and that's what I'd like to show you next. Let's just consider a single LC filter here. So pure inductance and a pure capacitance, and I have quite unrealistic values, but that's just for easy computation. And suppose we just excite this filter by a purely sinusoidal signal. And let's just take a normalized voltage of 1 volt, and we take pi radians per second for its angular frequency. Well, what do you think that would be the solution of this filter? What do for the current of this filter? And I posted 4 solutions here. And unfortunately, we cannot communicate so easily right now. But I don't know. Paco, do you see the chat box?
Yeah, the chat box is it's already there. Maybe you can write, or maybe we can read something. If anybody in the audience.
Let's call this A, B, C, and figure D. Which of the figures is the correct solution shows the plot of the solution for the correct current?
Yeah, it looks like the A should be the correct one. Looks like.
And other people, do you agree with Paco?
Let's give some seconds for the chat.
There's a slight delay in the chat box correction, yeah. Right? Which one is the correct one?
Fran Garcia said that the A option.
Okay, so that's 2 people for A. Anybody else?
Do you have any wild card, Dimitri?
A wild card? Yeah, I just give it a few more seconds. I'm curious. You can always gamble, eh?
Jose Ángel Sánchez González said A option. Alejandro said A option. Anyone else?
Well, I can already say that A indeed is a correct solution, but B is also a correct solution, and C is a correct solution, and D, they're all correct. And the reason for this is that here I have particular initial conditions on the current taken into account in order to get this nice, just purely phase shifted situation here. 90 degrees phase shift is what you see. And here I have zero initial conditions or just arbitrary initial conditions. And I can already tell you beforehand that this is the key issue here, and that's often forgotten. All these figures, they're all correct. Let's figure this out, why that is. Well, we have seen from session 1, I spent just a little bit of time on this, but you know this from just undergraduate studies, that if you approach this lossless LC filter from a frequency domain perspective of actually using just standard phasers, then this will be the admittance of this circuit. And this is well defined for all frequencies except the natural frequency. And the natural frequency is given over here. That's the resonance frequency of this filter. And so if you use phasor algebra, and I wrote it down here in terms of this rotating phasors. And by the way, I copied this from the paper, and there we used V for voltage. So. On the other presentations we used U, but what's in the name? So this is voltage. Then what you see, if you compute this in the phasor domain, let's say, and then you transform it back to the full time domain in terms of sines and cosines, then this will be the result. And there you indeed see that this is figure A. Yeah, that's what it suggests. But it's actually, there is an assumption here which you do not recognize from the equations. So let's go a little bit deeper into it. Let's just go to the physics. So then we start with the differential equation describing this circuit. This is just essentially just a Kirchhoff voltage law and then differentiated, right? Because I have to remember what was the definition of the natural frequency, and so you just have L the I dt, and then Q over C is equals the voltage. That's Kirchhoff voltage law for the circuit. So this is just the physical relationship of this filter. And then the forcing function in this case that will equal this, right? So now from the theory of differential equations, and keep in mind what I said in the first session, that phasor algebra has the advantage that you can avoid solving differential equations, but you have to be very careful. You have to be very careful. But let's look what happens. So the general solution of a system like this is given over here. And here you see, indeed, this particular solution, actually, which stems from the phasor analysis on the previous slide. But we get an extra part here, which is, let's say, the homogeneous solution, which is not taken into account by this phasor algebra. So what we need to do here, we need to determine what is A and what is B. And these are just real constants, but they depend on the initial conditions, for example. So if you solve for A and B, then you get the complete steady state solution in this case. Because, I mean, there is no friction, eh? So there is no, in that sense, there is no transient that damps out. And that's also the underlying physical reason why you see this homogeneous part in terms of A and B. And if you solve them, this is what you get. So here again, this is the phasor part. This is what you get with phasors, but all this stuff over here, it's also still there if you do not take any precautions. And again, this holds for the situation that the frequency in your input voltage does not coincide with the natural frequency. Otherwise, you have to solve the differential equation again. Otherwise, you get like a singularity here and there. So what you see here is that you get these two guys over here that are the initial conditions. This is just the initial condition for the current, and here I choose to start at t is 0, but you can also, of course, start at t is whatever you want. We can always shift along the time axis, and this is the initial condition for the rate of change of the current with respect to t, of the time derivative of the current. Okay, so these things, they will determine whether or not only this solution is valid, or that you have some other stuff that is not taken into account by phasor algebra. Okay, and if you look at this, then you can quite easily derive that in order to only have this solution, only have the phasor solution, you have to set these initial conditions. Well, this one is relatively easy. You don't have to do much. But this one is a problem, because in order to achieve purely sinusoidal steady state solution for your current, you need to set a non-zero initial current. So all the computations you see in all these papers dealing about power factor improvement using lossless LC filters, and the same holds if you have a more complex filter. I mean, then this equation becomes a lot more evolved, and then you have a lot of different resonance frequency. So then you need for each resonant let's say combination of LC stuff, you need to set their individual initial conditions. But that's not done. Nobody speaks about this, and I think I have like 30 just standard works, just books on circuit theory. I've been looking everywhere. I could not find this, and that was very, for me, very, yeah, the reason to write this paper. And when I was writing it, I was like thinking like, yeah, well, from a system and control perspective, this is obvious, and also in mechanical engineering books you find these things. But then I was sending this paper to the conference, and it was actually very well received. So I was like, okay, I mean, even though you do something almost trivial, then it seems to be forgotten somehow. I don't know. But this is very important. Otherwise, if you don't put this initial condition exactly like this, your phasor algebra is simply not valid. And if you implement your filter in a simulation program, then you will see that it doesn't work. Actually, it makes the situation a lot worse, perhaps. Okay? So yeah, I mean, how to do this physically? I mean, how to put an initial flux into, suppose you have a very expensive LC filter made by very expensive materials that they are almost purely inductive and almost purely capacitive. At the Meteorological Institute, they have these kind of standard devices that are almost ideal. And also that is, of course, what you want, because if you do power factor improvement, you do not want to put more dissipation in your system. You don't want to burn more energy than necessary. Otherwise, then the whole approach doesn't make much sense. And so you always want to design a filter with a very large quality factor, a very high Q factor. So with a very, let's say, as low as internal resistance as possible. So then, yeah, I mean, how to do this? Because I don't know how to put an initial condition on the current in an inductor. I'm not aware how to do this practically. Maybe you can add some current source. I don't know. Another thing is we know that for a linear inductor, the magnetic flux linkage is, of course, related linearly in this way. So then I have to put an initial flux to this inductor. I don't know how to do this. I mean, I have to put an initial magnetic field somewhere there. I don't know. And the problem is that, I mean, any additional, or any slightest mismatch you have here will result in that this A and or B will not be equal to 0. So then you will have this extra current component in your filter, which might make the situation much worse than before compensation. Yeah. And also, and that was I noticed when I was writing the paper. I realized this, that I mean, the natural frequency of the compensator will in general not coincide with an integer multiple of the frequency in your voltage, in your supplied voltage. So you can try this for yourself and put all the initial conditions to 0, for example. Then you will see that even subharmonic or interharmonic frequencies might appear. So then the solution of your current is not even periodic anymore. Well, we are still dealing with a linear and time invariant circuit. So in contrast to what you usually read in the literature, or what is being said, is that also linear time invariant circuits, which are subject to a sinusoidal input, for example, a voltage, might just exhibit non-sinusoidal currents. Okay, that's what this analysis is telling you. And of course, and again, I mean, this is of course an ideal situation where the inductor and the capacitor that are lossless. But in order to have like to make sense for power factor improvement, I mean, the resistance must be very low, so that even though there might be a little bit of resistance in practice, then still it can take quite a long time before this transient is damped out. And then in the meanwhile, you can inject harmonics into your power system that might excite other equipment to start resonating or to be disturbed somehow. Okay, so you have to be careful with this. And of course, what happens when the frequency of your input voltage precisely coincides with the natural frequency? I mean, then the filter is even unstable. So from a system and a control perspective, I mean, this system is not bounded input, bounded output stable, because the input here, the voltage, the blue line, that is a bounded signal, and the red one, the current, is unbounded in this case. Okay. Well, sometimes it makes sense to look a bit at in other engineering domains, and well, an intuitive mechanical analogy of a lossless LC filter is this mass spring system, where there is no friction here. It's like a almost perfect elastic spring here, and you have just a perfect mass. These are the equations, and well, you can just say that the mass that is like the analog of the inductance, and the spring stiffness that is the analog of the reciprocal of the capacitance. Okay, then you just compare it with the differential equation I presented before. And x here is just the position, and And F is just the forcing function you apply here. Okay, so then even though if you don't apply like a continuous force, but you just take this system, you just pull it out of its equilibrium, and then you let it go. Well, then you already have an oscillating system, and that oscillation that will just be persistent. That will not disappear because there is no friction. So it will just resonate at the natural frequency. Okay, and of course, when you start hitting the thing exactly at the same frequency or the natural frequency, then the whole thing will just collapse, right? Then you have like unstable behavior. So also for this system, I mean, phasor analysis is just not suitable to analyze this system, only under the very specific condition that you choose your initial position and your initial velocity in a certain way. Only then you get the correct answer for this system. How can you check this beforehand? And also, how can we have some kind of guideline that we don't make these mistakes anymore in our careers? Well, that appears to be the final value theorem, and maybe those who have been studying just classical control systems, they know about this, or it's often also brought to attention when considering the Laplace transform. Because now here S, I denote as the Laplace variable. And the final value theorem is saying that if you have some time function which is bounded on some interval here, then this equality holds. So if you take the limit of your time function for t, the time going to infinity, that is the same as in the Laplace domain as taking the limit of the Laplace variable to 0 and multiply the Laplace transform of your time signal by the Laplace variable. Now this only holds when if you look at the Laplace transform of your signal or of your admittance, then it's that there is no more than one pole at the origin, or no poles in the right half plane of the complex plane. So no unstable poles, because of course then you have an unstable system. So that will be definitely and lead to unbounded output behavior. But this is very important. This part, there can be no more than one pole at the origin. Well, if you look at an inductor in the Laplace domain, then you have this situation, right? Times I of S. So voltage in Laplace domain, the current in Laplace domain, and then this is just Ohm's law essentially, yeah, in the Laplace domain. So if you look at it like this, then I can say I of S is 1 over SL times VLS, and then this will be your input here indeed, and the current is of course the integral of your voltage. That's what the 1 over S is actually reflecting in the Laplace domain. A time integration in the time domain means dividing by S in the Laplace domain. And here you see that this is your transfer function, and you have just one pole, and that is in the complex plane, and it's over. If this is the origin, then the pole is over here. So for a single inductor, the final value theorem is satisfied. And then you can just do phasor analysis. And then phasor analysis just taking S to be just j omega, which means that the real part of S goes to 0. So that means that all the transients are gone. And then that S is j omega, then you essentially just go into the Fourier domain. Okay? And this is all fine. So for one inductor, it works fine. And if you have a capacitor, for example, then what you can do is that you take that the voltage of a capacitor is 1 over SC times, that's just the dual of an inductor, and this also has a pole in the origin. But the problem is, if you make a combination of two lossless elements, like in the lossless LC filter, then this will be the transfer function. And then the poles here are simply that S is plus or minus J omega n. So in the complex plane, you have two poles. That's a complex conjugated pole pair, but they have a real part in the origin. So this does not satisfy the final value theorem. So you cannot apply phasor analysis to this situation unless you precisely match the initial conditions, which is a very, very, very difficult task in practice. So just forget about it. Well, you can go a little bit further because that's how these filters are often used, of course. That's when you apply a non-sinusoidal voltage that you see a lot in many of these papers. And then, I mean, then you have this situation. So then you still have to deal with this homogeneous part where you have to assign the correct initial conditions. Yeah, so that will be highly sensitive to mismatches, and you can understand that in order to solve for A and B, you need all the information contained over here. Okay, and this depends on, so the initial conditions will depend on all the amplitudes of the voltages, on the frequencies, on all the stuff. So that is very, very highly sensitive to mismatches again. So I would actually just, I mean, there are literally hundreds of papers dealing with the situation, and then assuming that these initial conditions are satisfied, or they did not even think about it and just trust it on a straightforward application of phasor algebra when dealing with lossless filters or lossless networks in general. But you cannot do that. I mean, you have to take this into account. Otherwise, I mean, implement such a thing in PSpice or in MATLAB or in Simulink or whatever simulation program you have at hand, and you will see that generally you get a different solution than you would expect when just, let's say, bluntly applying phasor algebra. So what you need in order to guarantee a sinusoidal steady state in a linear circuit, as well as an unambiguous use of phasor analysis, I mean, you need time invariance, of course, but moreover, you need to satisfy the final value theorem. Okay? And when you implement lossless filters, you cannot avoid to set non-zero initial conditions in general. So I think that the whole application of passive or actually lossless filters in power factor improvement under non-sinusoidal conditions, I think it doesn't have any practical value. Maybe it has some educational value or whatever, but you cannot accomplish this in practice. You need to go into something more involved, like what they call active power filters or power conditioners. And active is a bit not really the right word, but let's call it then switched mode filter technologies, in which you mimic these kind of things. And with power electronics, you can do, of course, a lot of things. And there you can perhaps also mimic or synthesize initial conditions by just cleverly programming the switching patterns of your power electronics. Yeah, that's for part one. So I don't know if there's any questions so far, or maybe complaints even.
Dimitri?
Yeah?
I have one.
Okay.
So you're saying that phasor analysis, Fourier analysis, is maybe not the most complete tool So going from time domain to Fourier domain, and somehow has some deficiencies. So this is an important statement.
Yeah, I think it is.
All electrical engineers, yes, we were taught in the phasors, and for us it's an important tool. And as you have shown, there are situations where phasors are not applicable anymore. And as I mentioned the other day in private, maybe we are abusing of the Fourier transform, right?
Yeah. At the very beginning of the first session, I made a statement there, which was actually a bit of a slip of the tongue, and I think I was not very clear because I also got some questions in the via email about it. But what I wanted to say there was that suppose I have a Fourier series, yeah, like some frequency profile. Then if I would add white noise to that profile, and I do again, Fourier analysis, then I get exactly the same spectrum as the signal without the white noise. So there you already see that when you do frequency analysis, there is you average things, and you average things over a full period if you're dealing with Fourier series, for example, and that means that you throw away information. Of course, I mean, you have the big L2 and the small L2 space. They are one-to-one by all these transformations. I've been showing that as well, but that is for periodic signals for sure. But I mean, nothing in reality is periodic. That's also one of the biggest problems we are dealing with in the revision of the current IEEE standard, because there are a lot of people involved from practice, and they will never measure anything periodic. It's all subharmonics and interharmonics and all these kind of things. So, and here, I mean, this is of course a very simple example, but even with such a simple example, you see that the tools we learn in undergraduate studies, they are useful, of course, because it has brought us where we are now. We have been designing a lot of things with it, and it all works. But there are special cases that like this, that we often make simplifications or want to have things as ideal as possible, and then we must be careful. Then we must be careful. I mean, with the tools we use, it's the same that if you start using like a sophisticated tool, like a chainsaw. To hit a nail into the wall, I mean, that is not, it's not made for that, right? So we always have to take into account what are the limitations of the tools we use, and that should be taught as well, because I was pretty astonished that I could, in all the 30 books I have, I could not find it back. I could only find a lot of mistakes, actually. I was like, And for that reason, I wrote this paper.
So all these things must be in present in our minds when we are facing the problems with the power theory. When we are talking about reactive, distorted power factor, so we should take this into account. So why the power theory is not working in some situations, a multi-phase system? Maybe the answer could be the abuse of the Fourier transform. I think this is an interesting question.
I'm not saying that it's worthless, that you should totally abandon it, but you should be careful and be very critical about what are you doing with that particular tool. And don't stare blind, or don't trust what you read in a book.
Yeah. For example, we are always talking about harmonics, about subharmonics, interharmonics. They are all fictitious because they do not exist in reality. But this is because we've been told that the Fourier transform is a nice tool, it's a quite useful tool. But what would be happen if if we used wavelet transform, for example, if you wavelet, morelet, wavelet, hardlet, wavelet, something like that, that does it mean that we were talking that we have some wavelet current with some scale or something like that? So the question is, we should rethink about how we transform the time domain signals, like the voltage and current. Why we always prefer Fourier analysis instead some other tools, some other domains. So this is interesting.
Yeah, and I totally agree with you. That's a very good point. I think we should look further than our nose is long. They used to say, my grandmother used to say. But I mean, yeah, but that's what you see. But if you talk about wavelets and stuff like that, I mean, I think that will be pretty difficult to, let's say, sell to the power engineering community. The same you experience with geometric algebra, for example. I mean,
Yeah.
you need to be well willing to learn new tools.
Yeah, but we have to do something. We cannot
Sure.
We cannot go ahead to the wall over and over again.
No, for sure.